All right, guys, let's see. So, less than 130 cholesterol level, I expect 0.2 times 500, I expect 100. So make sure you put that in the right place. 30% of 500 is, right, I expect 130 to 200, I expect 30% of the population to have that. So 30% of 500 is 150. 200 to 240, I expect 35%. What's 35% of 500? 175, 11. And then it says 15% greater than 240, 75. And you can always double check and make sure that adds up. In this case, it adds up to be 500 people. I like it, or else hopefully you didn't lose anybody. So really, there's two main types that we see. We expect it to be uniformly distributed, which means it's evenly distributed amongst all categories. Or they have to give you a percentage for each category, and you can calculate for each category what's expected. Okay. How many did I observe? Well, that's when I started throwing this stuff in. 120 below 130. 200 between 130 and 200. I'm going to love it if I forgot to change the last one. 100 between 200 and 240, and then the rest. Oh, that's right. Good. I covered myself. The rest. So how many do I have so far? 420. So what's the rest? 80. I love it. I like it. Okay. So now you just start attacking. It's kind of nice. I'm hoping to God that it makes some sense how they constructed this chi-square number. Let's see, there's 20 different squared is 400. There's 50 different squared is 2,500. There's 75 different squared is 56, 25, and then 5 different squared. What? Where? There's 5 difference here, right? Yeah. 25. And then you take, how are we doing so far? Is it really cool? Okay. And then you just divide each of those by the expected. So be careful. You divide by the expected. So here this would just be 4. That's nice. Divide by the expected, not the observed. 2,500 divided by 150. 16.66. Okay. What is that? And then 5625 divided by 175. 32.143. Neato. And then 25 out of 75. 3. Is that cool? It's just 1/3, right? And if I add those up, I get 53 point oh something. All right? What do you guys think? 52? 53, right?
Yeah.
Yeah, 53.143. Sounds pretty big. What's degrees of freedom here? Yeah, so it's 4 categories minus 1, so it's 3. Alpha is 0.01. So looking at that chart, degrees of freedom is 3. Alpha is 0.01. I just get 11.345. I do believe that we kicked that test ass. 11.345. So what you guys got? That's your Z star, not Z star. That's your Z critical, your rejection region. And the Z star kind of equivalent is this dude. We got way the hell out there. So again, this is evidence that what? That the people in the secluded area have very different cholesterol levels than what we expect them to have. Which means what? Which means what possibly? especially the way I've written it, it's focused on one thing. So we know better than it's just different. They have what kind of blood cholesterol levels compared to the rest of us? Yeah, like here, they have much lower. We expected 150 here, there was only 200. We expected 100, there's 120. They have much, only. We expect more at the higher levels, and there was about the same, but there's definitely a lot more at the lower levels. So what might be going on that we want to investigate further? Yeah, so I mentioned the diet, so maybe the diet's different. Could be in the water, could be in the air, could be genes, right? Maybe nobody moves away, and they just have genetics that gives them lower cholesterol, right? Could be the amount of exercise they get. It could be a lot of things. So once I do this, I'm like, whoa, shit, let's descend upon that little area and see what the hell's going on. And just by going there, we screw them all up. Oh well, this happens. All right. Remember. I wanted to at least show you one little thing about how else chi-square can be used. You're only responsible for up through 11.2 homework. You guys hear me? Ooh, I got some interested people now. What? So up through 11.2. I'm going to make 11.6 extra credit. Yes?
Is this counting chapter 12?
Are you kidding me? So,
No.
so the order that it's in on the homework sheet, you're up through 11.2, which counts 12 because you got to go past 12 to get to 11. 11.
You're right.
Thank you. Every now and again. Don't get too excited. You're like, I don't have to do chapter 12 homework. No, of course. Yes?
Can you repeat that?
Okay. All right. Let me just say it like this. 11.6 is extra credit. How's that? Yes, okay. So let me show you, I want to show you one thing real quick, just because. Did I hear what I thought I heard? All right. So, I don't know if you guys remember, we looked at a different chi-square formula before. It's actually the more standard one. Goodness of fit is sort of a very specific kind of thing, but it's relatively easy to work through. It's a nice introduction to chi-square. There's another formula for chi-square that looks like this. So let me ask you, let me see if you guys remember. How do I construct a confidence interval for, for mean? So like this old formula, this guy here, right? So the reason that works so beautifully is because the z-score distribution, the normal distribution, is symmetric. What's right in the middle of a standard normal distribution? 0. So the formula is just stupid easy because they go up and down the same amount, right? If I wanted to make 95% confidence interval for the true standard deviation, let's just do that by itself. Let's just look at this chi-square chart. Let's say let's give ourselves something to work with. Let's say we took an n of 41. Okay, it should be on there. And I got S of, do it, Jeff, of 13.89. Okay, let's just use these numbers. And I want to make a 95% confidence interval for the true standard deviation. We don't have a formula that does that yet. So we're gonna kind of create it. So I'm going to help you a little bit if you want to do this extra credit, but I also just want to make you suffer through looking at this so you've seen it. Let's look at this. figure out how to do this. Mohammed. All right. So if I drew this picture, first off, what's the distribution look like? Can you guys draw that picture somewhere on your notes? Draw what the distribution looks like. At least some of you guys are like, what's wrong? Geeky Jeff will say Jabba the Hutt. Right, he's got a body and a big ass tail over there. Hello. That Han Solo can walk over. Okay. If I want to make a confidence interval, a 95% confidence interval, then somehow it's got to capture the middle 95%. But this looks messy compared to normal distribution, because normal distribution is symmetric. Makes so much more sense. This one still works the same way. It's just that there's not 0 in the middle. I'm not going to have a positive and a negative chi-square thing to work with. We're going to have what I call a chi-square small and chi-square big. We can actually figure these things out based on what we know. We know that 95% confidence, which means how much is in this tail, for example? 0.025. I like it, right? And then remember, the chart is to the right of what I want. So there's 0.025 to the right of this guy. This is one thing I want. I also want this guy. What's to the right of this guy? Oh, shit. Well, what's here? 0.025. So what's above it? In fact, you can kind of see it. 95 plus this, right? So it's going to be 0.975. There it is. All right. So the goodness of fit is a one-tail test. I don't know if you guys picked up on that on the ones we did. I was just drawing one tail because I had to be so far away. Confidence intervals are always kind of two-tailed deals. Please, dear God, notice that this is not set up in terms of one and two tail, because they wanted to be really evil with this chart for some reason. To the right instead of to the left, all this kind of evil shit. Did I give up for a little dude? Oh. So if I look up 0.025, I'm going to get what I call chi-square big, because it's the bigger value. What do you get when you look up 0.025? What's the degrees of freedom here? 40. I like it. Because now we don't have categories, right? So for degrees of freedom of 40, and you look at 0.025, where'd you go? There you are. I get 59.342. You guys also get that?
Yes.
Anybody still need one of these charts? Everybody's got one of these charts? Okay. So I get 59.342. What about chi-square small? Same idea, except now it's 0.975 you're looking at. Notice how nice this is, really, to be honest. Here's this, and over here is where I'm going to look, see if I look in the middle column, I'm going to look in the middle column here. Or not. Okay. So if I look down here, stop at degrees of freedom of 40, 24.433. Yep. And now, here's how this would work. There. So I use this formula one at a time. Now, what is it I'm trying to get a feel for? What is it that I know, and then I'm going to use a confidence interval to get a feel for what? What is it I'm trying to get a feel for? The true what? Yes, the true standard deviation, the population standard deviation, because all I know is S. Just like here, don't I find X bar, but don't I want to know what it seems like the true mean is? That's why I make the confidence interval, to get an idea of that. So that's what this does. Here I know S, and I want to know what the real sigma is. So what I'm going to do is interesting. I'm going to do, so what piece of this am I really interested in right now that I don't know? We just said it. What piece of this do I not know? We know these. We got 2 of these suckers. We're good there. We know n minus 1. We know S. We just don't know sigma. I'm trying to figure out what sigma looks like to be. So if I solve for sigma squared, if I solve for this variance, I get this. In general, right? That's in general. If I divide by the bigger chi-square, is the output going to be bigger or smaller than when I divide by the smaller chi-square? So dividing by a bigger number makes the result smaller. So my true variance is going to be between n minus 1 times s squared divided by chi-squared big and n minus 1 times s squared divided by chi-squared small. So this formula tells you what the variance is. I have 2 chi-square scores. So I'm really converting them into standard deviations. So if I just do this, do we have everything we need? What's n minus 1? 40, because n is 41. And what's s? I tell you. And you square it. And what's chi-square big? That. What's chi-square small? That. So you guys take a minute and try to finish that out. Just got to throw stuff in. Have one term on the bottom, so it doesn't need just 40 times. So we put it up here. So if I put true variance, oops. So this will be 40 times 13.89. It's the same on both sides, the top. On the bottom, it's just going to be the different chi-squares that relate to the bottom and top of the interval. Right? The reason the formula looks worse, 2 things. We're not used to chi-squared as much. That makes sense. Secondly, it's not a symmetric distribution. It's not going to look as pretty because it's not symmetric. Poor little dude. Right? So on the bottom here is going to be the big dude, 59.342, and on the other side it's going to be 24.433. So the variance is between those 2 things. What do you get when you do this? What do I get when I do that? Biggest mistake is to forget to square the poor little s. And another big mistake is to square this number. No. Chi-squared is this. So divided by 59.342. So I get 130.048 up to, let's see, divided by this guy now, 24.433, and I get 315.855. You guys get those? Some of you guys? The rest of you guys are like, you lost me at extra credit. Now, if I square root both of those, what's this a confidence interval for at the moment? Variance. So if I square root everything, I get a confidence interval for the standard deviation. So if I square root, oops, scheiße, get out of there. That thing, I'll get 17.772. And if I square root this thing, I get 11.404. So the standard deviation I got from the sample was 13.89. Is that in the middle of this? Is 13.89 in the middle of these?
Yes.
I mean, directly in the middle. Of course it's in it. Of course it's inside of it. But is it right in the middle of those? Oh, hell no. And why does that make sense? Because the distribution is not symmetric. It's going to go a different amount out on one side than the other. Yeah, I like it. So you couldn't have a problem like that one problem where they gave you the confidence interval and they said, what's the mean? You couldn't do that because it's not symmetric. It wouldn't be something you could do. Okay, maybe. That's another use. So if you do the 11.6, to be honest, it's not confidence intervals, but I want to show you this example. But you do use this as kind of like your chi-square star. You know, what you calculate in step 4. Where'd your sample get? How far did it get? Same way we did with the O minus E squared divided by E. It was sort of like a chi-squared star. How far did it get? Same idea. So if you want to do 11.6, I will warn you, it is hypothesis tests for standard deviations. All the same steps, it's just this is going to be the one you use to see where you fall. Okay? Let me see. So everybody's got a practice final, right? So number 11 is the one from, they use this chi-square stuff. Let me see, what was it? And somebody, what does a z-score of like 3 tell you by itself? Z-score of 3. What would it tell you about the data point? Yes. Someday, I don't know, someday I'll get everybody. Everybody's always like, can you tell me exactly what's going to be on the test? In this case, yes, I can, and I still get like half the people don't get it right. Drives me a little crazy. So on Wednesday we'll have review. So please, dear God, come ready with questions. We're going to make a final exam formula sheet. Cool? Oh, yeah. And I'll have the answer key for this practice final. Yeah. Sure. Please don't forget your keys.